think they're running the AC in this room. I'm not too sure why. One day they'll get the heating, cooling figured out. Well, it's official, folks. This is the last day. It's just us happy few. Hopefully a few more come in. But at the moment, let's just go through the standard announcements. We're working through this last document, so this is going to be our last one to get through for the course. If we don't finish everything here today, then I will come back to this document and upload all the rest of the solutions if you decide to come back here to use this as a study guide still. And for the other reminders, for the in-person section of the class, that's all that's here today. The final exam is officially Monday, December 9th, 8 p.m. to 10 p.m. in this room. So that's where I'll be. But I'll still extend that standard offer I mentioned earlier. If this is a pretty bad time for you, and I can see why that might be, that's tough to test so late at night. I'm also giving one that goes from 5:30 to 7:30 p.m. as well in this room. So if you'd like to join the earlier session, you're more than welcome to. Just send me an email so I know how many extra exams to expect, that kind of thing. And aside from that, other announcements are definitely be sure to check out this portion of the final exam information. Gives you a good indication of what you can expect. So there's going to be 6, 7, 8, 9, 10, 14, 15, 16, 17 questions altogether is what this is indicating. And these are all one-part questions. So I'm not saying there is like one question from section 11.8 with like 5 parts. That would be kind of rude. That's going to be just the total number of actual problems you'll be solving. Down below is all the other final exams that you can take a look at as well, and other final exam review information. And so at this point, we're about to finalize week 15. So congratulations, everyone. It takes a lot to get to this part of the course. I feel like we've been through a lot, but now we're here just doing some random calculus problems until we get to the end of this document, hopefully. Any questions or comments whatsoever before we start? Yeah. I don't have office hours on Monday, but I do have a meeting, let's see, early in the morning. So I'll probably be available on campus, possibly over Zoom as well. Send an email out and I'll be happy to join something like that. Other questions so far? Okay, so on this problem then here, problem number 12, we started off with a ratio test, then maneuvering through the ratio test. We carefully wrote down everything and carefully canceled, but a student from class noticed I forgot to carry this 2 there. That's always kind of unfortunate after canceling and forgetting something. So the 2 got duplicated to this part, and now finally this part. Once you get to this statement right here, we wanted 2 things, the radius and interval of convergence. We now have the radius of convergence. This number 2 implies it. To get the interval of convergence, that's where we mentioned there's going to be a lot of these extra steps. So we go down here. We broke down the absolute value, which gives us almost the same statement, but now it's a triple side inequality from -2 to +2. Subtracting 2 from both sides gives us this new expression. And now we go back to the original power series. This one is now just copied down below. And we have to test for convergence or divergence on 2 values, -4 and 0. Let me get my colors going here. So let's start at first. Let x be equal to -4. This is a generic power series. It's going to converge or diverge solely dependent on a value for x. And so we're going to test out what happens when it's -4 specifically. We plug -4 here by the red dot. We'll just get -2 to the power of n. So we have summation an, that's referring to the original power series, turns into a sum from 0 to infinity of -1 power n minus 1. Plugging -4 right inside here gives us -2 power n. And down below is n times power 2 to the power of n. That's hard to say for some reason. I think we've got it. This is our new power series. This one actually simplifies a little bit down the line as well. Right here, we can factor down the negative times 2 to get a sum from 0 to infinity. -1 power n minus 1. That negative sign there, we can factor out. That gives us -1 to the power of n, 2 to the power of n divided by 2 to the power of n. And so now we have a cancellation going this way. And a little bit more, we have -1 times -1 to the power of n minus 1. Let's resolve this part right here just as kind of its own problem. If you take -1 power n minus 1 times -1 power n, this will turn into -1 to the power. These things would just sum up. So it'd be n plus n, 2n, minus 1. And that's kind of an interesting statement. Imagine plugging in any number in there. If you plug in 1, you have -1 to power 1. That's negative. Plug in 2, you'll have 3 to power -1, still negative. Turns out any integer you plug inside there is negative. And that's because 2n minus 1 is odd for any integer n you pick. And a negative to an odd power just gives you negative and nothing else. So that's kind of interesting in a way. That's a pretty weird cancellation. We can take that, come back over here. And now the power series goes from 0 to infinity. The negative sign we can just put out in front. So there's where it ended up. And we have 1 over n. So this was a pretty weird series to test once we plugged in the value -4 and got this result. Simplifies down to just this. And this part alone is the harmonic series. It's known to diverge. It diverges to positive infinity. So if you have a negative in front, it still diverges for the same reason. It's just diverging to negative infinity instead. So we can start this one and just say, because this one is a known series, you could also use the p-series test if you'd like. This is the divergent harmonic series. And our conclusion is over for what happens at x equals -4. So we now know that we diverge at -4. Now we have to test what happens when x is 0 next. So we go and say, let x equal 0. We come down to our original power series and say summation an is now sum as we go from 1 to infinity. We're plugging 0 right here by the red dot, so that's just 2 power of n. Divide by 2 power of n, so that is a cancellation we're expecting. So now it's -1 power n minus 1. 2 to the power of n, divide by n times 2 to the power of n. New cancellation goes this way. And so we are dealing with the sum from 1 to infinity of -1 power n minus 1, divide by n. We can test this one as well using the alternating harmonic series, or excuse me, using the alternating series test, or we could just state this is the alternating harmonic series, which is already known to converge. So there's only 2 series really with names that we have known divergence, in this case convergence, and when those come up, you could just state the names of those, and that would count as the whole test. So let's say this is the convergent alternating harmonic series. So now that we've done all of that work, we just have to paraphrase. So we can say, up here, that was the radius of convergence, but it doesn't give us the full domain. The full domain is the interval of convergence, and we write it out this way. Interval of convergence, which we usually just label as I for short, goes from -4, but at -4, because we diverged, we put in, excuse me, an open parenthesis. A bracket would have said it's part of the interval, but that would have meant it converged at that value. Next, we go to this value at x equals 0. Down below, we had a conclusion of converges, and so we put a bracket on that one. So our interval of convergence, it's a half open, half closed interval from -4 to 0. The radius is 2 because that's half the length of this interval. And looks like we're done with this one, folks. This one was kind of tricky to get through, but any questions at all with the conclusions? Okay, and again, I think the weirdest thing about this one is, if this ever comes up, you're already dealing with a power series that's alternating, but you plugged in a negative value here again, it's alternating no longer because those cause a cancellation, resulting in -1. And so that's why this was a pretty tricky power series, I'd say, in my opinion, to get through. But when x is 0, it was a lot easier to get through the cancellation. So what we'll try out next is, let's see here, I kind of forget what is next. Looks like we're dealing with Maclaurin series next. This problem has no indication that you have to use the definition of the Maclaurin series. So that means any trick that you can use that works is valid. So it also provides a hint. Consider differentiating f first in order to come up with this power series. So let's do that. Usually if there's a hint in an exam problem, it's a good idea to try it out. Doesn't mean you have to use the hint. But let's start by saying if f of x is tangent inverse x, then f prime of x is going to be 1 over 1 plus x squared. What this reminds us of is this almost looks like the sum of a geometric series. We can in fact rewrite this and make it become 1 over 1 minus negative x squared going this way. And if we do that, here's the formula we're about to use. Anything that goes, excuse me, 1 over 1 minus x can now be rewritten as a summation from 0 to infinity of x to the power n, provided the absolute value of x is less than 1. So that's a formula that we're using. I believe this was in section 11.8, representation of functions using power series. So now down over here, we have the portion that's going to plug into the formula above. It'll be negative x squared going inside there. So this turns into sum from 0 to infinity of something to the nth power, excuse me, and that something is negative x squared. Hopefully my voice holds out for this last set. I'm pretty sure we'll get through it. So we're summing from 0 to infinity. Breaking this up a little bit further to make the next steps easier, we have -1 to the nth power and x to the power of 2 times n. This problem says state the interval convergence, but I had to change a heart on those instructions. Let's change this a little bit. On a real exam question like this one, I think the more typical answer would have been this. State the radius of convergence. So that's a usually way that this would be written. And the purpose for that is you do get the interval of convergence through this formula, but then we have to integrate. And when you integrate, you don't get to the interval of convergence. You just get the radius, which means you have to do a lot more work, this stuff right here, to actually get the interval of convergence. That's not something that we would have typically done on this kind of problem in that section. So we're just going to be satisfied on the radius of convergence, making it more similar to a real exam question. So we've got all of that, and we can say that this works provided that the thing we threw inside there in absolute value is less than 1. So it would go like this. Absolute value of negative x squared less than 1. This is some kind of interesting math that we're about to do. First thing that happens is the absolute value will wipe out that negative sign, and you just get x squared less 1. Now, we're trying to find the radius of convergence, so we need the absolute value of x right here. But if you take the square root of x squared, you do get absolute value of x. Square root of 1 is 1. And from this position right here, we have that the radius of convergence is going to be equal to 1, the same value that went right here, with that yellow highlighting, excuse me. So we've got the power series representation here by the red dot for the derivative of f, but we wanted the Maclaurin series representation for tangent inverse. So now we do this standard trick. We'll say tangent inverse x, that's the thing we want. It was indicated to be f of x, but you always can relate f of x to its first derivative f prime of x. The trick is integrate f prime of x dx. The only downside to this trick is you get a constant of integration, and you do have to solve for that constant. So that's the only downside. The next thing we'll do is take that whole thing, drop it right here. So now we're dealing with tangent inverse x is the antiderivative of a sum that goes from 0 to infinity of -1 power of n, x power 2n, dx. And that dx is super important whenever you write down an integral. It says what part is the variable, what part is the constant. Because of the dx right here, it means the only thing we're really integrating is x power 2n. -1 to power of n is regarded as a constant now. So this turns into tangent inverse x is now, let's put the constant first so we don't forget it, plus a sum that goes from 0 to infinity of -1 power of n. X is now to a power 1 higher, 2n plus 1. And we divide by that higher power, so that's all over 2n plus 1. So we now have Maclaurin series representation. It's a Maclaurin because where we look by the red dot, that's x minus 0 essentially, centered at 0, making it a Maclaurin series. The only last thing we have to do is solve for the constant c. On a real exam situation, if you guess that the constant c is 0, you're probably right more often than not, but that's not a guarantee. So these steps could be important. To solve for c, we use the center of this power series. So this is a good reminder that this is a Maclaurin series. And that its center is at a equals 0. So the best way to solve for the constant is you always want to use the center, because that's the one value you can plug in right there for x and get the sum of the total series. Plug in 0 and the whole thing is 0. So that's always a good call. So let's say tangent inverse of 0, that's where the center goes. We plug it inside right here. This will be equal to the constant plus sum as we go from 0 to infinity, -1 to the nth power times 0 to the power 2n plus 1, divide by 2n plus 1. But this is now an extremely fancy way to say 0. That means tangent inverse of 0 on the left-hand side is equal to the constant. But then at the same time, tangent inverse of 0 is 0. So we solve for the constant as well. So our overall conclusion on this problem is that the Maclaurin series representation for tangent inverse x, notice we never even used the core definition of the Maclaurin series, where you do one row of f, another row of f prime, and come up with the formulas. We just use the geometric series, but it's now equal to sum from 0 to infinity, -1 power of n, x power 2n plus 1 divided by 2n plus 1. And that's our answer. Any questions with that one, folks? One thing I forgot. This wanted at the Maclaurin series representation for tangent inverse. Well, we've got it down there by the red dot, but also said after a revision on instructions, state the radius of convergence. It's stated way over here, but the radius of convergence could potentially change if we integrate something. There's another theorem that says that's not actually the case, just the interval would change. So we should, at the very end, for our overall conclusion, restate the radius. because we're giving it for a different power series now, we should state it for this one here. So then that would finally finalize this problem right here. If you had your radius stated somewhere on the paper, I don't think I would nickel and dime you on points, but it's good to convey it right here. You're saying the series we were going for originally has the same radius. So let's go down below and try a new one next. This one is saying derive the Taylor series for f of x is natural log x at a is 4. And for this one, we do have to use the definition of a Taylor series. So this is a different kind of problem. The way this one starts off is a 2-column system. One thing you might notice though is when you did the homework and we looked at the lecture notes, there's not tons of examples of these kinds of things. There's, natural log, sine, cosine, e to the x, but you start to run out of really good examples pretty quickly. So if you just review the things that we've done and you've done in homework, you'll have a pretty good indication of what this question could be. There's not a lot of different varieties here. So here's our start. F of x is natural log x. The centered at a equals 4 means we do the following next. This is what makes it a Taylor series as opposed to a Maclaurin one. We calculate f at the center in this column, which just gives us a natural log of 4. Now we move down and start taking derivatives. F prime of x is derivative of natural log x, which gives us x power -1. We go over here, calculate f prime at the center. This will be 4 power -1. And this is just a rinse and repeat until we can detect some kind of pattern going on. So next step, f double prime of x. I left it in this format just so derivatives are easier to take. This turns into negative x power -2. So f double prime at 4 is negative 4 to the power -2. There's already a pattern that is emerging. It looks like on the first derivative, you have 4 power -1. Second derivative, you have 4 power -2. It looks like it's potentially alternating, except the first term is the odd one out. We'll have to write down natural log 4 as a first term, and then a power series expression for the rest of it. Let's go off to the third derivative. So f triple prime of x just moves a power -2 down, multiplying. So we have 2 times x power -3. On the right-hand column, evaluate the derivative, and we get 2 times 4 power -3. And there is a pattern that's emerging, but let's do maybe at least one more so we can really see it. Here is the fourth order derivative at x. You'll get -2 times 3 times x power -4. If we went down one more, it'd be 2 times 3 times 4. That looks like a factorial is what's coming up when you see those kinds of multiplications. So to the right, fourth order derivative at 4 is -2 times 3 times 4 power -4. So once we fill out a chart like this, the left-hand column is not as much interest. It's only used so we can evaluate and get to the right-hand column. And in the right-hand column, our overall goal is to write out what is the formula for the nth order derivative. So now any derivative we're putting down, any formula, evaluate at 4. To kind of get to that formula, we can look at our list and work backwards. We have something negative and a potential factorial right here. So on the fourth one, we're negative. On the first one, we're positive. That might suggest maybe going -1 power n plus 1. So this will be the n equals 0 index. On the n equals 1 index, we plug 1 in there. Yeah, it does come out positive, so we're on the right track. Let's just put down these indexes. Now that we started, it's weird to stop. Next thing we can see is, well, there's a 4 to a power. I think that's the next easier thing to put in. First derivative goes to 4 power -1. Second derivative, 4 power -2. So the nth order derivative should be 4 to the power of -n. The last thing we need to analyze is there's also a factorial. I think the factorials are kind of tricky on here, so let's extend this row. This one is a 2 times 3, so that would be a -3 factorial times 4 power -4. This is just a 2, so this is a positive 2 factorial times 4 power -3. Here we have a negative. You can think of that as a -1, and 1 factorial is 1. So -1 factorial times 4 power -2. And this is the weirdest one ever. We mentioned this a few times, but it's always good to reiterate. By convention, 0 factorial is taken to be 1. It's an odd convention in a calculus class, but if you take more math, combinatorics, it starts to look more and more reasonable, as strange as it seems. So over here, you have a 1 as well, and we can call that 0 factorial times 4 power -1. So now, looking at this pattern, fourth order derivative goes to factorial of 1 less order. Third order derivative is 2 factorial. If that pattern continues, the n here would turn into n minus 1 factorial. And that's our formula for the nth order derivative of this thing. Kind of nasty, but this is like our premier worst case problem in Calculus 2. So for this kind of thing, I'm pretty generous on partial credit. I realize this is not easy to do on a timed final exam. Usually you want to have some extra space to think about these things. So just knowing how to start it, giving me a chart of f and its derivatives, its evaluation, trying to get a formula down, that's a lot of partial credit on this problem, probably the majority of it. So even if you get kind of stuck on this one, leave your work there. I'll look at how you approached it and award partial credit based on that. But here's what the next step would be. Our Taylor series representation now needs the coefficients. Formula for the coefficient Cn go Fn at the center, which in this problem is 4, divide by n factorial. So this would turn into, we have the formula for Fn at 4. It's all this stuff here. So that plugs into this location, -1 power n plus 1, 4 power -n, n minus 1 factorial. Oh, I forgot my factorial. It's amazing what an exclamation mark can make a difference with on this algebraic expressions. And the denominator is just an n factorial, but because we're seeing n minus 1 factorial, we should expand that for factorial. N factorial can be rewritten as n times n minus 1 times n minus 2 times 3 times 2 times 1, which means it could also be rewritten as n times n minus 1 factorial. The n minus 1 factorial starts at this factor, moving all the way to the right. So where you see the n factorial, split that one off as n times n minus 1 factorial. And now we've got a good cancellation. Going that way, leaving behind -1 power n plus 1, 4 power -n, divide by n. This is always a good spot to try to simplify as much as feasibly possible, because at the end of this problem, you need to determine the radius of convergence on this thing, and unsimplified stuff is just going to make that limit a bit of a nightmare. Here's our next step, though. We can put this all together and say, not tangent, it was natural log of x. That's the function we want the Taylor series representation for. It's going to be equal to a summation, but let's be extra careful on that summation. Remember, we had some issues on these things. We wrote down a formula for Fn. If we look at our chart, it is only valid starting at 1. So let's be a little bit more specific here and say our row for Fn, let's say as a reminder, this is only for n bigger than or equal to 1. Same at the row for Cn, this is for n bigger than or equal to 1. And that reminds us that we have to go back up here, take the odd one out, natural log 4. That's indexed at 0, but it does not fit the pattern whatsoever. So we just write it out as a term all to its own. Natural log 4, the odd term out of infinitely many. Then These things are valid when we start at 1 and go off to infinity. So our summation goes n from 1 to infinity, which makes sense, right? You cannot plug 0 in for n at all any longer because of this n down below. So we have n goes from 1 to infinity of -1 power n plus 1, 4 to the power of negative n. Let's maybe simplify that one even a little bit more as well. We could just drop it to the denominator. I think that'd make it easier to work with. So we have n times 4 to the power of n. So that's our little Taylor series representation centered at 4. Only thing now we need is the radius. I'll leave that kind of hanging for the moment. Let's go down below and calculate the limit. That'll give that value. Any questions at all, though, getting through this? Yeah. Oh, absolutely. I'm not too sure where that went. That should have been x minus the center, which was 4, power of n. Thanks for spotting that one. Give that a little bit more space so it doesn't feel all crammed in. Yeah, it's supposed to be a power series in the first place, so that's a pretty silly omission to make. This is what makes it a power series, that fact that we have x raised to a power. And next, we'll come up with the radius just by using the ratio test on this thing. Any other questions so far? Okay, so here's our ratio test. We take the limit as n goes off to infinity of an plus 1 divided by an. So our numerator is going to be all this stuff to a power 1 higher. We'll get limit as n goes to infinity of -1 power n plus 1. Here we have a power n plus 1, but reflecting on how canceling these can be tricky and it's easy to lose stuff, let's write this in a slightly different way just to help with the cancellation. If that's raised to a power of n plus 1, you can also just write it as x minus 4 times x minus 4 power n. So it's like it's pre-prepped for cancellation when we put in the next fraction. Divide down below. Here it's an n plus 1. And let's do the same trick on this one. 4 to the power of n plus 1 is just the same as times 4 power n. Next thing we do is take a look at an. An is going to be the original terms all right here. So we multiply by n, 4 to the power of n, -1 power of n, x minus 4 to the power of n. And now we're ready to go with this thing. First, let's double check. Does that look right to folks so far? Okay, let's give this a try on the cancellation side. First cancellations I usually do is get rid of the alternating portions because they are just officially gone. Next, x minus 4 to the power of n, here and here will cancel off. 4 power of n, here and here cancels off. So all we've got left behind is 4. That's easy to miss. I think I missed the 2 on the last one. The n plus 1 in the n and the x minus 4. So we now have absolute value of x minus 4 times the limit as n goes to infinity, n divided by n plus 1. We can take the 4 and also just move it way out in front of the limit as well. And so that's going to be our limit through ratio test. I think this has came up twice now in its exact same format, n over n plus 1 in a limit. That's a limit of 1 exactly because that's its horizontal asymptote. So this turns into x plus 4 divided by 4 times 1. That times 1 is just the value of the limit that was evaluated. And if this is less than 1, implying convergence to the ratio test, that then would imply, if we clear the denominator here, the absolute value of x plus 4 is less than 4. So from this alone, we can move back upward and say, radius of convergence on this thing is exactly 4. And our total answer is now just on this line right here. You never have to box your answers unless you feel like you have work all over the place and you just want to signify right there in the middle is where the answer finally settled. Well, any last questions on this one, folks? Doing the Taylor series derivation? Okay, there'll be exactly one question like this one, and it'll either be a Taylor series, meaning you'll have a center of something non-zero, or it's going to say do the Maclaurin series derivation using the definition. That would imply you are plugging in zero into all of these. So really very, very similar kind of problem. They only differ by what the center would be. But let's then move on to the next topic. This completed really the major goal of chapter 11, dealing with the Taylor-Maclaurin series. So this is still chapter 11. Let's maybe come back to this one. This is a pretty important question, but really the bigger takeaway from problem number 15 is taking a look at our tests and doing more analysis on them, see how they work together. I don't think I'm going to ask a big concept question like this one. So if it's all right with the class, I think this is a good one to loop back on if we have extra time. That seem all right with folks? Okay. For all the questions that we don't get to, if this happens to be one, I am going to upload the total solutions to all of these on the Moodle website over the weekend. So if you want to come back to take a look at any missing problems, the solutions will be posted. So let's settle on this one next. This is the one from chapter 10. And just to give a pretty good hint on our chapter 10 problem, I think that this is a pretty similar one to what you can expect on the real final exam. I'm not going to do anything too major since we really didn't have a lot of time to get a lot of problems done in that chapter. So this is a two-part problem. In part A, we're calculating the first and the second order derivative. Let's take this opportunity to also just write down formulas. When you have something that's given parametrically, x is sine t, y is cosine t, and here's that parametric curve sketched, then the derivative dy dt becomes, the derivative dy dx is what I should say rather. Let me try again on that. The derivative dy dx turns into dy dt divided by dx dt. In a certain way, it's kind of a natural process. If there is an x coordinate and a y coordinate you're dealing with, and the derivative is a slope, your numerator should be the y value, your denominator should be the x value. So take dy dx equals, take the derivative of this one with respect to t, and through the chain rule, we get to -3 sine 3t. And the problem here, this formula rather, says take the derivative of x with respect to t, sine t will turn into cosine t. And halfway done already with part A. Next is the higher order derivative, d2y dx2. That one is a formula that's kind of similar. The derivation, in my opinion, is kind of tricky, but this is what the punchline is. d2y dx2 turns into d dt of dy dx. That is divided by dx dt. Note, when you do this kind of problem, you've already calculated dx dt once, so the denominator cosine t gets reused a second time on the higher order derivative. So let's calculate it down below here, just for the extra space. d2y is saying second derivative of the y function. dx2 is saying with respect to x both times, turns into d dt of, here we're putting in dy dx, so we're at this part of the formula, but dy dx is calculated in the line above, we're just dropping this down inside. So it's -3 sine 3t divided by cosine t. Down below is dx dt, which we've calculated once as cosine t. So this is our computation right here. Well, it's not as bad as it looks, but we do have to be kind of careful with it. It's a quotient rule in the numerator, and we also have an extra denominator. So carefully writing it out, it would start off like this to start. We have cosine t in the denominator. That came from right here. Now I'm looking at this portion. This is the quotient rule. So we have a complex fraction, there's no getting out of that. We have a numerator and a denominator. So if color coding helps, I might as well use it here. Quotient rule says differentiate the numerator. Through the chain rule, that would be -9 cosine 9t, multiply by the denominator, cosine t, subtract, copy the numerator, -3 sine 3t, multiply it by the derivative of the denominator. That's a lot of negative signs. That's a negative sine t. Then the denominator is this denominator over here to the second power. So cosine squared t goes here. So that's what we're looking at. There's a potential that some of this could simplify, but the very big simplification right away is if you have cosine squared and you're dividing by cosine t, visualize it this way. It's a fraction, you'll multiply by the reciprocal of that, which is just going to drop down below cosine cubed t. Up above, it's just a gigantic mess. Let's see if there's anything that here that could simplify. It's -9 cosine 9t times cosine t, and 3 negatives, so this is going to be -3 sine 3t sine t. There could be some trigonometric identity somewhere that could help us simplify this down further, but I'd say this is a natural stopping point on this problem. Simplifications aren't a major part of calculus. The major credit is always doing the calculus itself. So go for the easy simplifications you see. If you're ending up on a problem like this, where nothing seems to simplify further, you've got the right answer at that stage. Well, that's calculating two derivatives, the first order and second order. Next thing we're going to look at is when tangent lines could be vertical. Yeah.
What does d over dt equal?
This right here? Oh, that's just a Leibniz way of saying prime, essentially.
Oh, okay.
But it's saying it in a better way. It's saying you're differentiating with respect to the variable t specifically.
The difference in all of that?
Just that part right here, yeah.
Okay. And also, why is it -9 cosine 9t? Shouldn't it be -9 cosine 3t still?
Oh yeah, that was a weird copy mistake on that one. Yeah, the 9 there was good, but that should have been a 3. Thanks for spotting that one. Yeah. Let's see, any other weird little copy errors? Oh, down below here, it would have to change. That would be a 3t way down here on the very bottom. Once you find one mistake, I found there's usually others as well, so it's a good idea to look at it again. But other comments at the moment? Okay, so if you can do these two derivatives, you're on the great track for chapter 10. There's a follow-up question. Let's take a look at this one. We're being asked, at what points is the tangent line to the curve vertical? So we're only asking about the vertical tangent lines. That's kind of the purpose of why there's a graph in the first place. A vertical tangent line would occur here. Let's sketch it out just to indicate. Another vertical tangent line is here. And so just analyzing the graph alone, that gives us some great information. It tells us expect two locations or two values. Oh, no, 2 points that we have to find. That's going to correspond to vertical tangent lines. Looks like it's here and here, but we can't guarantee calculate it exactly just based off the graph. So we'll use calculus instead. So the idea with this one is we have a vertical tangent when the slope is undefined. That's what a vertical line would even mean in the first place, undefined slope. The slope is undefined when, let's take a look. This right here, dx dt, happens to be 0. So we go down below, vertical tangent occurs when dx dt equals 0. So what was dx dt? We can look up at the very top. That's x, so it should be cosine t. But it's also just right down here. You calculate that in the process of doing dy dx. So dx dt equals 0 would then imply cosine of t equals 0. On the number line, that occurs in 2 spots. And on the real final exam, that's kind of the purpose of this table right here. It gives you good information in quadrant 1, and then you can extrapolate through all the other quadrants. If you're using this to assist you, you would go down to cosine. Note the value occurs at 0, right at pi over 2. But you also have to note through trigonometry, there's a second value down here, 3 pi over 2 as well. So you might decide if you think it's a good assist for you on the final exam notes, putting the entire trigonometry wheel, if you feel like it's necessary, may not be a bad idea. But for folks that decide they don't need that, you could use this right here, quadrant 1. So cosine t equals 0 would then imply t equals pi over 2, or t equals 3 pi over 2. But even at this spot, that's not the full answer. We want the actual points on the graph. So we take those parameter values, pi over 2, 3 pi over 2, look towards the very top of the problem, where that stuff is. So we use the coordinates here to actually generate the points. So we'll say next, vertical tangents occur when the derivative is 0. That happens when cosine is 0, and it happens at those 2 radian measurements. So the vertical tangents are at, let's plug down 2 values. When t is pi over 2, we get our first coordinate. Plug pi over 2 in for x, that's sine pi over 2 for a 1. Pi over 2 in for y, that will be cosine 3 pi over 2, and that would become a 0. And let's take a look at that graph. Yeah, that was easy to kind of just spot right here on the graph. So this was maybe an easy graph for that kind of question, I would say. There's no guarantee on the real final exam, you can just read off the coordinate necessarily. So the calculus is probably going to be like necessary. But let's do this again. And when t equals 3 pi over 2, our second point is plug 3 pi over 2 in for here. That would become a -1. 3 pi over 2 here, let's see, that's going to be 9 pi over 2. But any odd multiple of pi over 2, cosine is just a 0, so that's a 0 as well. Let's double check. Yep, that's at coordinates -1, 0. It's kind of hard to see because that's not a really good screen grab of the graph, but it really was at coordinate -1, 0. So if you can get through this kind of questions here, chapter 10 is pretty much finalized. In real sense, then, we pretty much reviewed the whole course. What we want to do now is just do as many questions as possible with what's left on the document. Any questions at all, folks, on discussing those tangents? Okay, let's skim through here and just see what we've got. We are kind of low on time, so it's a good idea to be strategic. We've done a problem almost like this, but I think we used trapezoid rule. So there's some carryover there. That one's not totally new. We set up one for this one, so it's not totally new either. We haven't done this one. I'll leave it up to the class. Should we try this one next? A centroid? I don't think we've hit on this one at all. Okay, let's give it a try. Good call, folks. You could expect on the real final exam, there's a good likelihood of a centroid. I wrote this exam on Monday, starting to forget. So I don't know for sure, but I think I did put a centroid problem on the real final exam. So let's give this one a try. We want to find the exact centroid of the region bounded by the curve, e to the x, y equals 0, and the vertical lines between 0 and 1. In a real final exam question, I would produce the graph, so let's just do a really quick sketch here. Y equals e to the x. We're going between 0 and it's hard to find the home row on this one. 1, there we go. So here's our graph right here. Horizontal line y equals 0 is just this one, and the vertical lines x equals 0, x equals 1 close off these two locations here and here. So this is about what you'd be looking at if this was the real final exam question. Let's add those extra marks. So we have here x equals 1, here x equals 0, horizontal line is y equals 0. So this is the region we're considering. Imagine it's maybe some kind of particle board with uniform thickness, uniform density, and you're trying to balance it under a pen. You need the coordinates of where that's exactly going to occur. That's exactly the problem we're doing here. First thing you need is the area of this region, which means you integrate from 0 to 1, the original curve, e to the x. That's a fast one. This is just going to be e to the x, evaluate from 0 to 1. You get e power 1 minus e power 0. That means it's just e minus 1 on this problem. For a problem like a centroid on a final exam, I don't think I want to make the antiderivative too nasty because it's already kind of a big process. So now at this stage, we're finding the coordinates of the centroid. First, the formula is x bar is the reciprocal of area, same limits of integration, 0 to 1, but we take x times f of x. And y equals f of x is e to the x in this problem. F of x is just what's mentioned as a formula. We have to infer that they're referring to the y function up here. So 1 over area is 1 over e minus 1. That just looks kind of weird, but it is exactly what the quantity would be. Integrate from 0 to 1 of x times e to the x. And out of nowhere, that's an integration by parts problem. Let's get a table going for that and maneuver through it. So in integration by parts, we want u to be x, dv to be e to the x dx. du is the differential, so it's just 1 times dx, just a dx. Phi is an antiderivative, but the antiderivative of e to the x is itself. And then that says, coming back down over here, dropping the line, x bar. Let me fix the color coding first. X bar is going to be equal to 1 over e minus 1. We need a bracket because now we're putting an integration by parts on this integral right here. So this has to be allowed to distribute through. So we'll go u times v, that's going to be x e to the x. And it's evaluated from 0 to 1, minus the definite integral from 0 to 1 of v times du. That'd just be e to the x dx. Notice also that integrate from 0 to 1 e to the x dx. Try to always look for ways to not reinvent the wheel. We've solved that once, so we're just going to substitute e minus 1 directly here, not forgetting to distribute the negative sign. So it looks like it would have been a nasty one, but x bar is mostly computed at this point. It's 1 over e minus 1 to start. In the brackets, we're starting our evaluation. That'll be 1 times e power 1. That's just e. Minus 0 times e power 0 is just a minus 0. Minus this integral we solved earlier, which is e minus 1. So we have 1 over e minus 1. This is e minus e plus 1. So it's done at that stage. It's 1 over e minus 1 times 1, which is 1 over e minus 1. It's a good call, though, because you'll have a calculator available to see if that is even reasonable as an x-coordinate. 1 over e minus 1 is about 0.59, close to 0.6. It would move slightly to the right here. I would believe that. That looks about right. A long rod or something at that coordinate for x would balance this board, is what this is saying now. So we turn it over and now do y bar next. Any questions at all, folks, on getting the x coordinate?
What would you calculate on
It came out to kind of close to a 0.6. I've got here a 0.58. Actually, that's pretty good to actually put on paper, really. We're going for the exact value, but it's a good idea when you do these problems to really look into the graph. That's why it's provided, just to see if it's reasonable. It's rare to have such a nice visual check like that, so it's worth taking advantage. Next up is y bar. First, we'll start with the formula. 1 over area, integrate from 0 to 1, 1/2 times f of x squared dx. So that's our formula for the second coordinate now of the y bar, or of the centroid rather. Reciprocal of area is the same, 1 over e minus 1. And we also have a half here. We can pull that out to just put it out in front. So I'll go times a half. Integrate from 0 to 1. F of x squared means you're squaring this e to the x all the way at the top. That's going to be e to the power 2x then, dx. So this integral is even easier. You could use u substitution on this one, but because it's a linear function of the variable, this one's a good one to do just right away by hand. So this turns into 1 over twice e minus 1. Let me zoom back in on this. Times antiderivative of e to the 2x is e to the 2x. But because of that 2 right here, you just multiply by a half again and visualize this right here. If you differentiated it, you would get e to the 2x times 2 through the chain rule. Times 2 clears off the 1/2. So we have the right antiderivative at that stage. We still have to evaluate it though. So this goes from 0 to 1. I'm putting these extra parentheses here because this is a very good strategy. You don't want to copy all this stuff twice. Leave it factored out to the left and just do the evaluation for e to the 2x. So we now have 1 over 4 times e minus 1 multiplied by e to the power of 2 times 1 minus e to the power of 2 times 0. So this is altogether e squared minus 1. That goes up into the numerator. Divide by 4, e minus 1. That's kind of a curious problem, actually, because e squared minus 1 actually legitimately factors. That's a difference of squares. You don't have to do that, but it's kind of tempting. This is e plus 1 times e minus 1. Divide by 4 times e minus 1. Giving just one extra cancellation, so that y bar is e plus 1 divided by 4. Let's also approximate that one just to see if it's even reasonable in the first place. E plus 1 fourths gives us a value of 0.93 approximately. Let's come up here. 0.93, that sounded concerning, but you know what? That seems about right, actually. It'd be just shy of here. And that looks about right because this area, in this 4 unit squared area, is bigger than this area that extends out with that slope. So I would believe that that looks plausible as the second coordinate of the centroid. So we can say as an overall conclusion, that construction, whatever it is, has exact centroid, center of mass, at 1 over e minus 1, e plus 1 over 4. So that's the full process for the centroid question if it comes up. I think it's a pretty high likelihood on this exam. For some reason, I feel like I really did ask one. I don't remember what the problem was though. But let's see if we can do another one to finish off the day. Any last questions at all for this one? Okay, next on the list, let's try to pick a good one that can fit in the time we've got. I've got a long list of just random series. We did kind of do a good set of series already. Some stuff with comparison tests, alternating series tests, and so on. We have done one of these, analyzing interval of convergence for a power series like this one. You know what? We haven't done that one. 27 is a separable differential equation. That one is new as well. 28 we did do. This one is a first order linear differential. So we'll see if we want to do it after 27. But I feel like this is a problem that we have not yet done. Let's go for this one here. So I'd claim it's a separable differential equation, but you know, you really have to kind of figure that out by separating it in the first place. The reason I assume it's a separable equation is first order linear differential equations are typically written in this kind of way. But if you have x's and y's kind of mixed like this, that's kind of a giveaway. It's probably separable. First step we want to take is Newton's prime notation is no good to us, so we convert it to Leibniz notation, dy dx. If this is separable, we're going to consider y in blue, x in green, and the objective is to get the blues and the greens on one side of the equation. So we have in the numerator, x times y. Denominator, we have x squared plus 1. So looks like the way this separates is in one step. We should divide by y and multiply by dx at the same time. Division by y will give us a 1 over y dy on the left-hand side. Multiplication by dx will give us x squared plus 1 dx. And at this stage, it's totally separated. Everything involving y on the one side, everything involving x on the other. So we integrate both sides. And left-hand side is an immediate formula. This one is the natural logarithm of the absolute value of y. Right-hand side, you have options, but if you look at it really closely, you might be able to just visually inspect and say, it's going to be some kind of logarithm. But if that's kind of weird work for you, our author sometimes says he has done it by visually doing a u substitution. If that just seems kind of odd, you could just really do the u substitution. So let's do it up here. X over x squared plus 1 dx suggests a good u should be the denominator, x squared plus 1. The differential du is then 2x. dx, I'll clear off the 1/2, multiply it by du, leaving x dx. So back up here, I'm doing this in orange to kind of signify if you know the answer because you've visually done a u substitution, that is an acceptable thing to do. So this is optional work, but still good refreshing material. So the dx becomes 1/2 du. X dx is gone, replaced with that. We have 1 over u, replacing the 1 over x squared plus 1. So this turns into 1/2 natural log absolute value of u, which then turns into 1/2 natural log x squared plus 1. Due to x squared plus 1 being always positive, it's up to you. You can drop the absolute value here. So finally, what that says, we have an antiderivative. This side right here is 1/2 natural log x squared plus 1 plus a constant. Now it's said to solve the differential equation, give an explicit solution in terms of y, if possible. It's possible. So we have more work to do, unfortunately, on this one, but it's good review work as well. The next thing we can do is go e to the power. Maybe probably the better next thing is see if we can put this on a second page. Okay, we've got space now. We're going to go e to the power of the left-hand side, which is going to be natural logarithm, absolute value of y. It'll be e to the power of, this one's a little bit tricky, so let's take this power. Properties of logarithm says it can turn into an exponent. It would become a square root x squared plus 1 inside there. So now it's e to the natural log square root x squared plus 1. The reason I took that step here is if we left 1/2 in front, there is no cancellation. It's pretty surprising. The natural logarithm has to have a coefficient of 1. We also have a constant there, but we can handle that with a different property of exponents. So first up, on the left-hand side, just absolute value of y. On the right-hand side, we can go e natural log root x squared plus 1. I just noticed an extraneous parenthesis. Let's get rid of that. And it's multiplied by e power c. So that's just properties of exponents. We have a great cancellation here. So now absolute value of y is now equal to e to the power of c times the square root of x squared plus 1. So far so good. Next thing we need to eliminate is the absolute value of y. But if you eliminate that, you could say y equals plus or minus e to the power of c times the square root x squared plus 1. So c is an arbitrary constant, any real number. And for the folks who have really looked closely at these differential equations, there's one thing that's extra tricky about this. This is not all solutions. There is one specific solution that is missing from this thing. And you can kind of see what it would be by looking up here, or looking down here and observing plus or minus e to the power of c is never 0. It does not matter how hard you try putting in a right constant to make that happen, you will never hit 0. So my solutions over here are for everything that involves a multiple of root x squared plus 1, except the 0 function. That's the thing that's missing, because if we come up here and say y equals 0, actually, let's use a more official pen here. If y equals 0, then the left-hand side, y prime, would be equal to 0, and the right-hand side, x times y, x squared plus 1, would also be 0. This implies y equals 0 is a solution. So plus or minus e to the power c is every single real number except 0. That means our total answer, when we combine this and this, gives us one overall solution. We typically call it the general solution. Is y equals, now we're just going to go c, an arbitrary constant times root x squared plus 1. Because once we establish 0 can work as a solution, we expand on this thing, which is a way to say all real numbers except 0, and just now say any real number truly was valid. 0 is a solution in particular. So this one is kind of a nasty overall separable equation. If you stopped all of your work, say right at this stage, I think I'd probably award most of the credit on this one, because the rest of it is just kind of tricky finicking with algebra and other really niche things with a differential equation. But this was the last question I think that we didn't actually hit on that will be on the final exam. So that's probably a good stopping point for us as well. Oh, sorry, it was this right here. So for all the remaining solutions that are left here that we didn't get to, I will come back to them over the weekend and upload them. So take a look at these, possibly sometime around Saturday. I hope not to do it on Sunday, but at some point, one or another, I'll get the solutions posted to each one of these. Well, have a great weekend, folks. I do realize that it's the most pivotal weekend of the semester. So if you do have questions while you're studying, don't hesitate to reach out. And on the day of the exam, Monday itself, I have a meeting with the department chair starting out in the morning, but then I'm free for most of the afternoon. So if you have questions, if you want to connect on Zoom, don't hesitate to reach out or email. I'll be very available on Monday. But have a great weekend, folks. Try not to work too hard, try to get extra sleep, that kind of stuff. And we'll be back at it at 8 to 10 p.m. in this room. If 8 to 10 p.m. doesn't work, just send me an email. I'm offering another one in this same room, 5:30 to 7:30 as well. You're all welcome to join. But have a great weekend. I'll see you all on next Monday.